Hi guys, welcome back to my channel. In the last video, we were looking at growth curves, and in particular, we were looking at logistic growth. And as I mentioned in the last video, initially, if we were to have some sort of curve or some sort of growth, after a particular point, if we have logistic growth, this is going to start to slow down, and that's this curve here that we see in black. And the reason for that is because this has some sort of carrying capacity as a result of having either limited resources or limited space. So this is different to exponential growth because with exponential growth, after this point, exponential growth actually continues to rise. And that's because it's not being limited by other factors. So how do we determine whether or not growth is exponential or logistic? So what we can actually do is we can actually find this point, and this point here is actually at half of our carrying capacity, so P over 2. Now, from this point here, so from 0 to P over 2, so that's our value for our function here, this curve is actually going to be concave facing upwards. After this point, when we have logistic growth at least, so from P over 2 to, well, the end of time, to P, I guess, then this is going to be concave down. Now, the difference between the logistic growth curve and the exponential growth curve is that at this point, if it's exponential, this will actually continue to be concave up. So what that actually means is if we can find this point of inflection, then we can determine if this is concave up or concave down after and before particular points. So because this is a stationary point or a point of inflection, I can say we can do this using the second derivative. So just as a little refresh, if we have a maximum, so like we can see for this red dot here, the first derivative is going to tell me the location of those points of inflection or maximums or minimums, whereas the second derivative is going to tell me whether or not they are a max, min, or a point of inflection. And the way that we can do that is because when this is a maximum, the second derivative, I'm just going to do the dashes just to save myself some time. So the second derivative is going to be a value that is negative. So in other words, a value less than 0. If we have a minimum, then the second derivative is actually going to be positive. So it's going to be greater than 0. And if we have a point of inflection, so one of those times where it's positive, 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 starts to slow down, becomes 0, never actually goes negative though, continues positive, then the value of that second derivative is going to be equal to 0. So let's go ahead and let's do an example to see if we can find whether or not this is going to be a logistic growth curve or not. The number of pigeons in a park is described by the equation y is equal to 200 over 1 plus 99e to the power of negative x over 2. Where y is the population size and x is the time in weeks. Determine the rate of growth of the population. So to determine the rate of growth, we're going to find the first derivative of this function. To do that, I've rewritten this and I can substitute in u for my inside function here. Once I've done that, I can use the chain rule to determine the derivative. So here I've got my derivative. So the rate of growth of the population is going to be equal to 100 multiplied by 99e to the power of negative x over 2 divided by 1 plus 99e to the power of negative x over 2 squared. Question B, determine the coordinates of the point of inflection. So to find the point of inflection, that's when the second derivative is going to be equal to 0. So I've rewritten my derivative because what I'm going to go ahead and do is I'm going to go ahead now and find the second derivative so that I can find the point of point of inflection. And so this time I might actually use the product rule where this initial value here is going to be equal to my u and this product here, or this factor here is going to be equal to my v. All right, this got a little bit crazy, but I've just sort of used some colors to help see what's going on. So like I said before, I've used my product rule where this equation here is equal to my u and this equation here was equal to my v. And v prime u plus u prime v is going to be equal to that next derivative. So lastly, let's just go ahead and let's simplify this. I think I can do that by making these denominators the same and simplifying that way. Lastly, I know because of my multiplications earlier that these are probably going to have some factors in common. So let's factorize out. Let's try factorizing out this 4950 because I'm pretty sure this should be able to fit into both. You know what I'm realizing? I'm going ahead and I'm trying to simplify this expression, and I really don't need to, because the whole point of this is to find when this is equal to 0. So 0 is going to be equal to all of this. So what I could do automatically, I could multiply both sides by the denominator, and that would remove that, and then divide both sides by 4950. So I'd end up with 0 is equal to 198 e to the power of negative x minus e to the power of negative x on 2 minus 99 e to the negative x. So we can go ahead now and we can actually solve this. It's a lot simpler to solve. I don't know why I was spending so much time rearranging. Okay, so gone ahead now, and this does have an inflection point at x is equal to 9.19. So let's substitute this back into our original function to determine the population at this time. So substituting into my original equation, I get y is equal to 100. Okay, so what that means is, so since that was our point of inflection, if this was indeed logistic growth, right, that's going to happen here at p over 2. And we've determined this value here to be equal to 100. And that's going to be when our time, so our value for x, is equal to 9.19. Whoops. Okay, so to answer that last question, determine if this is a logistic equation or not, what we can do is we can examine points before this and we can examine points after this. Alternatively, we can also graph the original expression to see if that is a logistic curve or not. So to do that, we can pick any x value before this point and we can see what the value is and whether it's going to be a maximum or a minimum after these points. All right, so to do this, I'm going to test two values. I want to test a value beforehand, and I'm expecting that since this is concave down, I'm expecting that when I substitute x into my second derivative function, that this is going to be a positive value for my second derivative test. I'm expecting when I test my second point at x is equal to 10, that that is going to be concave up, and so therefore pretending it's kind of like a maximum, the value of my second derivative should be negative at this point. So I'm going to substitute these values in and I'll write the solutions here. By the way, you can actually check this using a graphics calculator or by using some sort of graphing tool, or you could do this by substituting x into your calculator. So when x was equal to 9, this is the value that I was hoping would be a positive, because that would suggest that it would be like this, concave down, and it was. So that means that it's met the first criteria for my logistic equation. Now the next criteria is that after this point it has to be concave down, concave up, which means it's going to be a negative value, and it was. So therefore, because of that, this is actually a logistic equation. And when you graph the original equation, you can actually see that. So just something to be aware of, when we have something that's in this form, that's pretty much indicative that it is going to be a logistic equation. Alrighty, so that's how we determine using our second derivative test to determine whether or not a function is exponential or logarithmic after a certain point. Because if it's a logarithmic function, it's going to be concave down until the halfway point of the carrying capacity, and then after that point it's going to be concave up. Whereas if it was an exponential function and it was continuing to rise this way, then that would continue to be concave down. So we would expect for that second derivative test to indicate that this value would be positive after that point. All right, let's summarize today's lesson. So we find out the point of inflection using the second derivative test, because the second derivative will be equal to 0 at the point of inflection. Before this point of inflection, for any given x value before this point, the curve should be concave up. So in other words, the second derivative test should be positive before this point. After this point, it should be concave down, and so therefore the second derivative should be negative after this point. And this point is the halfway point of the carrying capacity. All right, so that's how we determine the difference between exponential growth versus logarithmic growth curves. See you in the next video.